more commonly, as I said last time, we are dealing with unknown variances and standard deviations, and we have to make a decision as to whether or not we believe that the standard deviations should or should not be equal. That allows us to either pool or not pool the variances. And those are the two different versions. If we adjust the variances with our pooled idea, then we're okay. And I can do something like the following. Page 374, we're given some summary statistics. Do a two-sample test for equality of means, assuming equal variances. That phrase right there. That's what tells me I can do a pooled variance. The first one here is comparison of GPAs for randomly chosen college juniors and seniors. In group 1, we have an average of 3.05. There are standard deviation of 0.2. And there are 15 people in that group. In the second one, we have an average of 3.25, standard deviation of 0.3. There are also 15 in that group. We want to do a left tail test. The left tail test means I'm thinking that my difference is what? I'm going to copy down all this information so I have it. Oh, there's one other piece of information I need out of that original statement. It says do a test for equality of means. If I'm testing for equality of means, that's the same as saying that the difference between those two means is this should not stop the room, people. I'm testing to see if these two means are the same. What's the difference between them? Zero. Remember, our benchmark is the difference between the two means. So I need that for my calculation of either Z-calc or T-calc, depending on the setup. Whenever I see the phrase assuming equal variances, I'm going to use a pooled setup. So, before I start computing anything, a left tail test. Left tail test means what? A null hypothesis, I need an alternate hypothesis. The choice of my hypothesis depends on the type of test. Doing a left tail test. What's the null? What's the alternate? Greater than or equal to what? And which mu? So what expression goes here? What goes on either side of that? Ah, I'm testing to see if the variances, to see if the means are equal. So I'm testing to see if their difference is greater than or equal to the benchmark. The benchmark here is 0. And that means that my alternate is that it's less than 0. That makes sense because that's the left side. So yes, remembering left tail means the null is greater than or equal to is exactly the good thing. The alternate is the less than because that's the left side. But I have to remember what I'm testing. And the two hypotheses, normally when we were just doing one, we say, oh, well, the mean is either equal to or greater than or less than a number. Here it's the difference between the means is benchmarked against that number. Okay. These are all S's. There's no sigmas. I'm using a pooled variance. That means I need a t-value. If I'm doing t-values, I need one other piece of information to do my t-values. T's all come with degrees of freedom. Because I can't look up anything on my t-table without knowing which degree of freedom I'm in. And in this case, degree of freedom I'm in, well, that's based on number of people. Now, I don't know which group is juniors and which group is seniors in this pile. It would help if they told me that so I'd know which way the grades are going, but I don't know. What I do know is that group 1 had 15 and group 2 had 15. So my degrees of freedom takes 1 away from each group. So there are 28 degrees of freedom in this problem. Good. With that in mind, I need to compute my pooled variance. There was a formula for this we gave on Friday. What's SP? Pooled variance. Which S squared? If it's N1, so S1 squared will be 0.2 squared.
Plus N2 minus 1 times S2 squared
0.3 squared.
over N1 plus N2 minus 2, so the degrees.
Yay. A number I already worked out. Wonderful, beautiful, fabulous. Somebody give me a number. Okay. Now that's our variance, not our standard deviation. There's a square there. If I wanted the standard deviation, I take the square root of this, but it uses variance, not the standard deviation, in my formula. Now I can actually compute my t calculated value. T-calc is the difference in the means minus my benchmark over square root of, and it should be standard deviation over number of people. It should be variance over number of people. S squared over N1 plus S squared over N2. If we were not separating the variances, that would be S1 and S2 respectively. We combined them, so it's SP in both cases. But numerically, I have all these numbers up here. 3.05 minus 3.25 minus 0 over, we just came up with SP, 0.065 over 15 plus 0.065 over 15 again. Again, I need a number. Yes, you should be getting a negative number.
Negative 2.148.
Sounds like a good negative number to me. Why would I expect to get a negative number here? Well, the top of this fraction's negative. X1 minus X2 bar, right? And X2 bar is higher. So yeah, I expect a negative number out of this. The bottom is the square root of a positive thing. It's always positive. Top is what gives me my sign here. And we were testing to see if a left tail. So I would expect t values to be negative if I want a left tail. What do I do with this? Great, we got a number. So what? What did we do with our t-tests when we were just doing one? We do our z-tests. We do the same thing for all of them.
Compare them to see if our hypothesis is correct. For our null hypothesis.
To see whether I keep it or reject it. Yes. But I need to compare it to something. What's the something I compare it to? Compare it, the appropriate value on my table. which I get from what was the alpha given in this problem? I wrote it down. So I go to the 0.025 for a one-tail test, and I go down until my degrees of freedom reads 28. There's my number, 2.048. I'm going to write that down. That's my critical number. Now, the problem is this number is positive. All the numbers in my table are positive. The assumption in my table for one tail is that tail is the right tail. So I'm doing a left tail. What do I do? You have two choices here. How to deal with this.
Subtract it.
From what? I'll give me -1 something. That subtraction works for probabilities. This is not a probability. This is an actual line on the graph. So unfortunately, that isn't going to help me this time. What else could I do? The same thing we did when we were doing single samples. The fact that this is two samples doesn't change what we are doing. I need to know if we're in the rejection area. In a left tail test, that's here, and a right tail test, that's here, and a two tail test, that's here. How do I know whether or not I'm in that rejection area?
I think you have to count X, yeah, it's that.
That's okay, either one.
If it's greater than or less than your critical T value.
But there's a problem with doing that with these numbers. -2.148 is absolutely less than -2.048.
Isn't it the absolute value?
Bing. That's the piece I need. In which case, I'm not looking for less than an absolute value. I'm looking for greater than. The other option is to say, oh, this is assuming we're doing a right. The graph is symmetric. Make it negative. Just subtract it from 0. So what I could do is I could say, oh, well, we'll use the z critical that's -2.048, and then this is further left than this. So I can say, oh, t calc or t stat is less than t crit, so I reject. If I look at absolute value, I'm always looking for greater. It is completely your call as to whether you take the absolute values or you remember, oh, I'm on the left, flip the picture. As a matter of fact, at the top of our Appendix D page, you will notice there's that little picture, and it's really hard because it's all faded on my copy. But if I go to the actual back of the book and I look at Appendix D, it's got this picture at the top that looks like a right tail. So I know I just need to flip the picture to do a left tail. I need to make a better copy before I give you one for the exam. I reject my null hypothesis, which means what?
The mean one minus the or difference between the means is less than 0.
Okay, So my conclusion is that there is a difference in the means. Mean for group one is less than mean for group two. It would help if, again, if I knew which group was the juniors and which group was the seniors, so I could figure out, is there like senioritis setting in? Or are these people like, I got to go get a job, I need better grades, and pushing themselves harder? I don't know which group is which. Now, there is another way I can decide on accept or reject. Does anybody remember what that method is for the z-tests that we did last week? Or the one sample t-tests that we did last week?
Value to the A, whatever the A.
The alpha by significance. I need a p-value. Problem. P-value means looking up this number on our table with the right degrees of freedom. This table is not complete enough to let me do that. So I can't do a p-value check with this table. I could do a p-value check in Excel or in one of my other technologies. You know, like this. Because under our stat button are those tests again. And one of those is a 2-sample t-test. And I can do this based on the data I was given. In Excel, I cannot do what I'm about to show you because Excel doesn't let me give it the means and the standard deviations. It only lets me give it raw data. But here, if I go to that 2-sample t-test, I can tell it I want to give it the statistics. And I can type in the average and standard deviation in number of people in group 1, the average and standard deviation in number of people in group 2. See the little arrow over there next to where it says N2? That means there's more crap. So I keep going down. Hey, look at the way it's written the null hypothesis. It wants to know, are we testing for it to be equal to, less than, or greater than? It's actually writing the alternate hypothesis. It wants to know, are we doing a two-tail, a left tail, or a right tail? And it's using the alternate Halley rather than the null hypothesis to write it. And then it wants to know, hey, do you want this data pooled or not? Do you assume there is equal variances? I said yes. And then I told it, hey, do the calculations for me. It even tells me the degrees of freedom. And down here where this arrow is, it's showing me all the same numbers. It's actually showing me a couple of extra numbers. Notice that if I go up to the top here, though, it gives me the t-score. The same t-value we calculated by hand, negative 2.148. But underneath that, it doesn't give me t-critical. It gives me the p-value. And the p-value is 0.0202, which is less than 0.025. If p is less than my significance, I can reject my null hypothesis. Same exact result, but I didn't have to look up the critical value. If I keep going down, it gives me the standard deviation for the pooled behavior. We got 0.065, that's the square. This is the square root of 0.065. Do I need it for anything? By hand? No.
If we use this method for the testing instead, is it okay to just say use calculator?
You better tell me what you wrote, what test you used and how you did it. Yes. Please write instructions so I can recreate what you did. Because what will typically happen is someone will say, I used my calculator, and I'll try and do the same thing on my calculator. I'll go, what the? So I want to be able to make sure I can do what you say you did. I'm going to do this test again. And now I'm just going to change one thing. I'm going to change pooled from yes to no. At the end of class on Friday, did I give you the weird version of the DF when we have no pooled variances? Did I write that one down or did I only? Okay.
I just looked at.
Okay. So what happens if I don't pool my variances? Well, if I don't pool my variances, things get ugly. We assumed equal variances. If I don't know that the variances are equal, now two guys named Behrens and Fisher noticed that this caused a problem and wanted to adjust for it. But rather than adjusting T, what they did was change the degrees of freedom. So notice that looks just like my pooled variance formula. Only instead of SP, it's got S1 and S2. Because I can't put them together, I got to keep them separate. Here's where it gets ugly. Welch came along and said the right way to deal with this is to change what distribution you're using. Adjust your degrees of freedom. Mother. That shouldn't be one line on the bottom there. Those should be separate fractions. Welch's contribution usually results in this turning out to be a fraction. So whatever number I get for this, I then round down. I am the first person to tell you that I hate this formula. The white hot passion of 1,000 suns, I hate this formula. I don't want to use it. And by using a summary calculation ability, I don't do this directly. So if I switch this from pooled to not pooled, instead of having a degrees of freedom of 28, I'm going to use whatever the degrees of freedom come out of this. And I'm going to keep these variances separate. And lo and behold, my degrees of freedom is now 24.4, which means I would round down to 24 on my table. I still got the same P, the same T. I got a slightly different P value. Why? Because when we lower our degrees of freedom, the tails get fatter. And so our P value goes up. In this case, it didn't go up enough to make a difference. We would still reject because that's still less than 0.025. I get the same result with an unpooled variance. More people in real statistical analysis use this version because they cannot make the assumption about the variances of the two groups being equal. If I happen to be pulling two different samples from the same group, well, then there's only one variance. I can assume they're equal. I am 100%, again, happy to do this in technology. There are several examples on our Canvas page done in Excel. In which case, when I go to compute the p-value, I'm looking it up with my t-distribution. Especially when the two groups are the same size, this is nicer because that fraction in the denominator is uniform. I don't have to have equal sample sizes. It's often useful that way. The pooled variance and the unpooled variance become the same when the sample sizes are equal. Even if I don't have known variances, if my samples are big enough, I can use S instead of sigma. Even if I'm doing z-scores, because I've got a large enough sample, I can assume the central limit theorem. And that allows me to use normal distributions. This gives closer results to the t-test. It increases the slight chance of a type 1 error, a false positive, but it really does work fairly well. Let me pull up one of the Excel examples. Here's what we are told in problem 9. For a marketing class term project, Bob is investigating whether college seniors eat less frequently in fast food chains than freshmen. He asked 11 freshmen, 11 seniors to keep track of how many times they ate in a fast food restaurant during the month of October, assuming equal variances. Again, an assumption. Can you conclude that the mean is significantly smaller for seniors at 5% significance? Okay. Are seniors eating at fast food restaurants less often than freshmen? So, I have all this data. Let's create a test out of this. Here's the advantage in Excel. If I go to the data tab right here, all the way over on the right, it says data analysis. When I click that, this is where I got histograms, right? But notice what comes up is a list of options. And right there on the page in front of me, it says t-test, 2 sample, assuming either equal or unequal variances. I can do it either way. It told me use the assumption of equal variances, so I'm going to use that. And if I click on this, okay, it's going to ask me where stuff is. Where's the stuff for variable 1? We said seniors eat less than freshmen. So if I let population 1 be the seniors, population 2 be the freshmen, my alternate hypothesis is less than. Mean 1 is less than mean 2. And that means we're doing a left tail test again. Variable 1 range. I click in the middle of this. I click on this little highlight box, and it allows me to highlight the data. Enter. Variable 2 range. Same thing. By the way, you see this thing here says labels. If you highlight the words as well, senior and freshman, it'll label each set of data with that name, and then you have to check this little labels box. Hypothesized mean difference. My hypothesis is that they're either equal or they're not, so my mean difference should be 0. Alpha, 5%. It said the 5% level of significance. That's right there, 0.05. I'm going to ask it to put the workbook answer that it creates in a new sheet. You could just stick it somewhere on this page if you want. I'm going to ask it to put it in a new page. Here we go. Here's what I got. You'll notice it shows variable 1, variable 2 at the top. If I'd used labels, it would have seniors and freshmen. The average for the seniors, because that was variable 1, is 10.6. For the freshmen, it's 14.1. The variances are given, number of observations. Hey, it even does the pooled variance for me. I'm going to make this column a little bigger. Now, I called it T-calc. You called it T-stat-M. There it is as T-stat. So that's the calculated T-value right there. Am I doing a one-tail test or a two-tail test? Doing a one-tail test because I want to know if it's less than the left tail. Which means I need information that's one-tailed, not two-tailed. So what I actually need information on is right there. All of that says one tail. There's a critical t-value. There's also a p-value. Do I keep this data, this null hypothesis, or do I reject it? Reject or fail to reject? It's a yes, no question, people. Do I reject the null hypothesis? Yes, I reject it. Why? That's why we have to know what kind of test we were doing before we started. We were doing a one-tail or a two-tail? We're doing a one-tail, so I'm only looking at that highlighted set of rows. You said, yes, I should reject. Because? Exactly. The alpha, the significance on this test was 0.05, and that p-value is 0.04. That's a reason right there. The other way to think of it is to take the absolute value of the two different t-values. The t-calculated value is 1.8. The critical is 1.7. I'm too far out. I must be in the rejection zone. I use either version. By the way, I decided to do this test again with unequal variances. Again, that's available here under the, wrong button. Cancel, close. That's another option available here, unequal variances. And if I do that, I still reject. But notice it changed my degrees of freedom. I got the same calculated t-value, and I got the same t-critical value. and my same p-value. There we go. Questions? The acceptance or rejection of a null hypothesis in all of these cases is equivalent to saying, if I built a confidence interval around the true difference that I was looking for, that benchmark value around 0 in our case, then I would say, oh, I'm at least this confident. But I take my exact x1 minus x2 bar. That's my estimate. So for the GPA problem, that was negative 0.2. And I build the confidence interval around that. If 0 is in the confidence interval, then I don't reject my null hypothesis. Because it could be that they're equal. If 0 is outside my confidence interval, then I can reject. But that means I should be able to build a confidence interval. So we have to figure out when we're doing a t-test what the t-value is to build our confidence interval. We take our benchmark. That's the estimator for our benchmark. And then we add or subtract t alpha over 2 times our standard error. Now, the standard error depends on whether we assume equal variances or not. If I assume equal variances, you'll notice that big first square root, that's got the pooled variance. And then it's divided by the number of things. That's standard error. Variance over the square root of number of things. S over square root n. That's exactly what I should be seeing for my standard error. But if I have not equal variances, then I'm just going to use the two variances separately. But I must change my degrees of freedom. That's nasty looking. But how do I use it? Let's go back to problem 1, where we did our seniors versus juniors on grades. I'm going to put back up my numbers here for a second. Ready? We had all of this stuff. So I need these numbers again. X1 minus X2 bar was negative 0.20. 3.05 minus 3.25. We had degrees of freedom of 28. And we had alpha being 0.025. Now here's where I cough a minute because I realize what I need is T of alpha over 2, right? And that should be 0.0125. I don't have 0.0125 on my one-tail section. So I'm going to use 0.01 instead. I got to cut it in half. I don't have the exact half. I'm going to go down. So either I have to look this up using technology, or I can use alpha being 0.01, alpha over 2 being 0.01 instead. So with a degrees of freedom of 28, alpha at 0.01 is 2.467. I'm using this formula up here. The number under this square root is the same number we used for our pooled variance. So I know that number. Negative 0.20 plus or minus 2.467 times the square root of 0.065 times the square root of how many people were in each group? Back in that problem. Turn the camera back on, damn it. 15. So I'll have 1 over 15 plus 1 over 15, which gives me 2 over 15. And now I can grab my calculator and get a number. .467 square root 0.065, come out of that square root, multiply by the square root of 2 over 15. That's my margin on either side of negative 0.2. Hey, wait a minute. If I add, what number do I get? I get 0.0297. If I subtract, I get negative 0.4297. Is 0 in my confidence interval? Yes, it is. I cannot be 100% sure based on just the confidence interval that I would reject. Our test, on the other hand, said reject. What's the difference? I used a bigger t-value. Because I used 0.01 instead of 0.0125, that might have made the difference. It's really close. Zero's right on the edge there. The other thing we can do is we can do a version for the first sample and a version for the second sample. If they overlap, then we might think that the difference between them is 0. Page 377. Again, there's an example done, all worked out on our Canvas page. More on Wednesday. We'll see you all then.